Hi, my name is Zeyang and my pronoun is she, her, hers. Now, Kostiantyn and I, on behalf of other co-authors, will be presenting our state-of-the-art report on the use of embeddings in visual analytics. We are from Linköping University and Linnaeus University in Sweden, and here is the team. This talk consists of 5 parts. First, we would like to explain the motivations for doing a start on the topic of VA plus embeddings, then explain the explicit scope and a little bit of methodology. After that is the main part, and we'll talk about some interesting examples and highlights we find. And then we'll talk about data-driven analysis based on our categorization. Last but not least, we'll present the research challenges and opportunities. Now let's get started. The title of our paper is VA plus embeddings, and the term VA stands for visual analytics, which is probably why you are watching this video. But as we set out on this study, more and more visual analytics papers started to mention the term data embeddings over the years, along with some other related keywords showing on the screen such as word-to-vec and BERT. The semantics of the word embedding varies under different contexts. In this survey, we explicitly refer to embeddings within the visual analytic context as the process or the results of projecting or representing data entities onto a lower dimensional space, where the similarities of points reflect their semantic closeness in the original space. Both the resulting embedding vectors and the spaces are referred to as embeddings. You probably have already seen the term or the concept appearing many times under different contexts, such as in natural language processing, where approaches like word embeddings and sentence embeddings are so fundamental for text representation as inputs to different language models. In machine learning, embeddings are ubiquitous in concepts such as representation learning, in designing and learning joint embedding architectures or somewhere else or everywhere else. And of course, for visualization research, which is the basis and the context of all the discussion happening in this talk, classical dimensionality reduction techniques such as TSNE are used everywhere. However, within the visual analytics context, as we examined in this survey, embeddings are actually used beyond simply projecting some high-dimensional data onto a 2D screen. Here are some examples of things that can be associated with embeddings. For example, representing text like our survey article in word embeddings, or embedding graphs into numerical vectors using random walks, transforming those machine learning datasets into features representing your cat images, or embedding the audio of me talking right now. If we stand from the perspective of trying to add some human-in-the-loop process to embeddings, there is both a need to explore relationships within the embedding space and interpret the embedding process. That is where visualization or visual analytics naturally step in to explain a rather black box process or a high-dimensional space. But on the other hand, introducing embeddings and integrating embedding into a VA pipeline is equally common and important. It often appears during the data transformation process of a visual analytics pipeline, but is never limited to the pro-processing steps solely. As we discovered, embeddings are not only based on the choices originating from the need to acquire non-numerical data and to perform new type of joint analysis, but moreover, it leads to the creation of customized visual encodings and interactions. Respectively, the high-level analytic tests, the design of evaluations, the usage context, the target users, actually, each identifiable component of the entire VA system is associated and influenced by the initial choice of integrating embeddings. So we have 2 initiatives in writing a state-of-the-art report on the use of embeddings in visual analytics systems. First, this is the timely and hot topic. There are simply just more and more VA research has started to mention the word embeddings and are actually using embedding technologies in their systems. On the left is the number of papers included in our survey, and you can see an increase over the years. There are also already rapid advances and progress in embedding technologies. But at the same time, the semantics of the word embeddings are highly heterogeneous. You see the term appearing everywhere under different contexts. Correspondingly, for each VA system, embeddings are used in a unique usage scenario under very diverse downstream application domains. Our state-of-the-art report aims to provide a systematic overview not only for those of you into visual analytics research and curious about how embeddings are integrated, but also for others we commonly call domain experts if you are in some particular domain such as urban science, but are interested in getting an overview of how embeddings are used for VA systems supporting your particular domain-specific research questions. We are also providing a visual browser accompanying to our paper. Click the link below, you could see all the examples. You can search for keywords and filter out items according to our categorization. I think the browser can be a good inspiration source or for educational purposes as well. The link and the QR code will also appear on the last slide of the presentation. Well, we briefly talked about the motivations for us to write such a survey, but still visual analytics plus embeddings sounds kind of vague, and the concept seems to be applicable to many papers. So we would like to refine it explicitly for this state-of-the-art report that we only select papers that meet one of the criteria stated in the slides. Embeddings are explicitly represented in at least one visual representation and were explicitly computed within a VA pipeline. Also, to exclude papers that just use dimensionality reduction techniques to solely compute the 2D, 3D, or 3D plus time layout on the screen, the resulting embedding space should be more than 4 dimensions. In a sense, our survey is based on the word embeddings in visual analytics, and we put a restriction on its semantics and context. As a result, we first selected approximately 1,800 papers based on the keywords in different peer-reviewed databases, and then we take a detailed look and got 122 that matched our criteria mentioned before. The search is beyond these venues, and the topics are very diverse. Based on the annotations of our corpus consisting of 122 papers, we now want to present our categorization scheme and analysis based on the annotations and statistics. We derived the categorization scheme based on how the integration of embeddings would influence which part of the VA pipeline. But first and foremost, to acknowledge the diverse set and the usage context, we summarize the trends of the use of VA plus embeddings in 8 identified domains in this paper. We referenced multiple sources such as the ACM computing classification system to come up with 8 domains. On the left, you can see the distribution of those 122 papers that would fit under one or more domains. Based on the categorization, we are actually able to identify further fields such as urban visual analytics and social media analysis. And in our survey article, we talk about trends within each field and insights across different domains. For the statistics, you can see that we label a lot of papers on machine learning. It is not surprising how the word embedding is closely associated with so many machine learning models. Additionally, it is not a one-to-one mapping, so for many applications, for example, a visual analytics tool using graph neural network for drug discovery, we assigned it into 2 categories. Here is an overview of our categorization consisting of 9 different top-level categories. A more detailed analysis and justification of our categorization scheme can be found in the paper. For the rest time of this talk, following the order of our categorization, we will talk about some insights and statistics of our annotations. For instance, what are the target users of those VA tools? What are the common input data types? We will also talk about some of the embedding-related computational details, as well as high-level visual analytics tests associated with them, novel visual approaches, the ways users can interact with those embedding views, and the evaluation of the tool. The first question you might be asking is, who are those VA plus embedding tools made for? Even though there is great diversity in usage contexts, such as the figures on the left showing a work embeds code stack trees for visualizing anomalies of function executions in high-performance computing, or the ones on the right embedding table tennis strokes in their VA system. According to our categorization, we observed that majority of papers only mention the word users in the introduction when they try to describe the target user. Even though there are many implicit hints about their motivations, domain-specific research questions, and potential usage contexts, only 32 out of 122 papers have explicit target user descriptions, such as domain experts, and even fewer papers mention the background knowledge required for their target users. The panels highlighted by the yellow rectangle are the embedding views. We only take partial screenshot of the user interface, but you can already see that embedding-related panels are only one of the supplementary views. Two common ways for papers to mention the scope of target users are expert interviews before development and post-development evaluations, including usage scenarios, user studies, and quantitative measures. Besides some commonalities that might be applicable to every VA tool, we discovered that a few authors mention some criteria when deciding on their user study participants. Even though the target users may be from a specific domain, such as medicine or just game players, they are implicitly required to have some basic concept of machine learning, using software for patient data analysis, be computer science major student, or student who understands statistics and intrinsic dimensionality. As a result, adding embedding-related panels may require users to have a certain level of knowledge to be able to use the tool effectively. But not many authors mention explicitly who their target users are, and much fewer authors mention the background knowledge needed for their target domain experts. And we can only infer some of them in their evaluation and user studies when they are selecting participants. While under some contexts, adding embedding-related views that try to get a taste of the underlying data distribution would mean adding further requirements for potential users. For a smaller collection in our corpus, from another perspective, embeddings open up opportunities for creating personal visualization that enables data analysis in a personal context. Although users may have different backgrounds and goals, the creative visualization aims to encourage all of them to experiment with it. For such cases, embeddings help mitigate the knowledge gap by indicating semantic similarities within and across different datasets, allowing users to infer unknown concepts based on their existing background. For instance, the figures on the left propose an inspiring approach that uses embeddings to create metaphors that link one data entity to another, so that even though users might be unfamiliar with one dataset, they can infer it based on their understanding of another dataset and explore the unfamiliar dataset easily, since the mapping between those two datasets make users with explicit knowledge about the data item also gains implicit knowledge about all other data entities that are semantically similar. The examples on the right, along with some other similar papers, also use embeddings to make users' exploration experience more efficient and serendipitous by indicating the redundant data attributes and highlighting the underexplored subset of the dataset. The next question for those visual analytics systems is, how do those tools compute the embeddings? And most are BERT autoencoders and word-to-vec models. Correspondingly, tests are the most common input data types. It is no surprise that so many test visualization papers are included in our corpus, Since we are selecting papers based on searching explicitly the keyword embedding, which commonly appears in phrases like word embeddings, when thinking about integrating some algorithm from natural language processing into the VA pipeline. We are aware that many other V4ML techniques might refer to some similar motifs of embeddings, but with other terms such as latent representation or feature space. But they are out of the focus and selection criteria for this survey. Even though a big portion of the papers in our corpus is related to machine learning and tests, we could observe a great diversity in data sources, and a common motivation for integrating embeddings in their VA pipeline is because their data is multivariate and heterogeneous, such that other more typical ways to represent data might not suit the need. For instance, some authors would argue using dynamic time wrapping might be insufficient to compare time series, and they choose to use autoencoders to embed time series as feature vectors. As those examples shown in the slides, like failure reports, audio data from urban noises, code dependency graphs, or crime data, the corresponding VA tools need to use embeddings to perform data representation, and adding an embedding-related panels act as an intermediate step to visualize between the downstream metrics and the raw data distribution. Compared to the diversity in data sources, we see the choice of computational methods are quite similar. According to our annotation, the predominant method is still BERT, word-to-vec, and its variant, such as node-to-vec for embedding graph data. The histogram in the middle is the screenshot from our survey browser. The filled yellowish color shows the distribution of the use of something-to-vec technologies for each year compared to the outline of the bars that shows the overall yearly distribution for those 122 papers included in our corpus. We can see that, for instance, in 2022 last year, 11 out of 39 papers named their embedding techniques as something-to-vec. Specifically, 6 papers use word-to-vec, 3 papers use node-to-vec, along with other extensions, variants, and customizations. For the examples at the bottom that aim to create a visual analytics tool identifying city crime hotspots, the authors propose hotspot-to-vec as one important computational module for their visual analytics tool in analyzing crime data. They use autoencoders to embed time series, and the grouping and projection of the feature vectors are used to guide the users to find relationships between crime events and geolocations. We could see there are 2 ways to integrate embeddings into a VA system with both heterogeneous and homogeneous data. The first is about embedding one data type and getting the distance metrics, and at the same time using other methods to get a bunch of other metrics. A combination of those metrics determines the visual layout. For instance, the tools on the right shows different ways that visualization charts can be represented as dots in the scatter plot. They incorporate word embeddings of tagged keywords in the meta label of those visualization charts, along with some other chart encodings and dimensional intersection information to aggregate pairwise distance such that similar charts can be clustered. In such cases, an ensemble calculation of different metrics with user-customized ways determines their positions. On the other hand, a very small set of papers is trying to project all the features, heterogeneous data or multimodal data, into a joint embedding space. The figures on the bottom left is one example that maps image, labels, 3D shapes into a shared semantic space. The dimensionality of embedding vectors is one of the choices that can be made while computing the embeddings. As seen from the results on the right, it seems that the choices between 50 and 500 dimensions is the most common choice and which might be sufficient. However, according to our categorization statistics, many publications do not specify the dimensionality of the used embedding vectors, nor mention the details of other hyperparameters. Further, the authors are not paying enough attention to evaluate the computational components, which can be an important influential factor leading to a truthful, credible visual representation. There exist many natural language processing papers arguing that embedding-based word similarities are sensitive to small changes in the training corpus. For many visual analytic tools that aim at addressing a domain-specific problem and providing its insights to viewers, the need for more specification of computational components, together with the hidden instability of the chosen computational method, would hinder the reproducibility, transparency, and credibility of their work. Now we would like to shift the focus from the computational component to the visual component. In our survey article, we have included all visual components that aim to show information from the embedding vectors or data from direct vector calculations. And it is not surprising that the predominant visual representation is 2D projection scatter plots. 76 out of 102 papers are using 2D projection as their main visual representation of embeddings. The bar chart on the bottom shows how many papers provide interaction technique support to the embedding-related panels. There exist some papers that use DR plots with no explicit mentioning of where users can interact with the chart. For many cases, a scatter plot representation of embedding seems to be enough, but it is not sufficient if we want to encode contextualized information associated with those embedding vectors into a visual representation. There exists a smaller set of papers that try to augment the scatter plots by adding glyphs with Voronoi maps. Well, a common motivation behind it is to deal with uncertainties arising from the projection of the dataset or the partitioning process. Creating either overlapping or non-overlapping partitions on the screen is often a way to augment the charts in order to communicate contextualized information. The following two visual interfaces are two interesting examples that use such augmentation methods, but their high-level visual analytic goals is to try to infer the global geometry of the embedding space and highlight potential clusters of areas of interest. But there exists other level of granularity for providing a different lens to view those embedding spaces. So besides viewing the global geometry using some scatterplot 2D projections, another common need is to explore the local neighborhoods further to compare different neighborhoods. The figures on the left provides a neighborhood overlapping view displaying the number of similar neighborhoods in two embeddings, along with some other metrics reflecting properties such as spread and density of neighbors. Besides that, a small set of papers aims at finding semantically meaningful directions within the embedding space, as shown in the figure on the right. For word embeddings, many NLP papers are investigating the cases of whether two word embedding vectors being added up can point to the third word. Here on the right figure, the authors try to review the relationships for analogy words in the embedding space by creating links between those data items. Similarly, we also found some papers in the field of social media visual analytics to review connections of smaller user groups or attribute features. As a result, adding links or parallel coordinate plots to show such correlation or connection. Besides those three general tests, viewing global geometry, exploring local neighborhoods, and finding semantically meaningful directions, we also created a more detailed category of visual analytic tests associated with those embedding panels. Here is the distribution of those papers fall into one or more of the following tasks. It is not that surprising many works using the embeddings to represent data entities, but also for comparison, selection, and exploration. And all of those tasks are deeply connected to the aspects of the intrinsic support embedding space can offer in terms of global and local geometry patterns. When we think about how to interact with embedding-related panels, besides other more common user interactions, such as selecting a point on the scatter plot to show details on demand, one thing that might be unique to embeddings is that it can be an effective way to summarize a large-scale dataset based on the clusters in the embedding space, such that users are able to explore in a hierarchical fashion, and not all the data need to be displayed all at once. In the representative figure below, users are able to refine and merge multiple clusters. When navigating through a large-scale dataset, essentially if the higher-level embeddings already show all the features of interest, it is unnecessary to generate a complete representation of the entire dataset. Computing the embeddings plays a role in summarizing the data and also offers a way to explore it with different resolutions. Another primary interaction associated with embeddings is not about exploring the embedding space, but about using embeddings to recommend to users what might be the next relevant items to inspect or select. Usually the visual representations is simple, like a list, word cloud, or some bar charts that recommend a few close neighbors for users to explore. This interaction links back to the target users in one of the previous slides that embeddings are useful to guide user interactions. But as we observed, the majority of techniques using word embeddings like word-to-vec to provide keyword suggestions. And the ways of displaying and interacting with recommendations are rather limited. Given those interesting VA systems, it's important to evaluate them properly. However, as stated, we found that not all techniques evaluate their computational components, even though the visual layout is heavily based on the computational results. Furthermore, according to our annotation, most authors care about the usefulness and effectiveness of their tool, and only a few very limited cases some authors put explicit emphasis on the stability, learnability, and sensibility aspect of the proposed visual analytics system.
Based on the collected survey data, we conducted further analysis with the overall trends and patterns in mind, rather than focusing on individual example approaches. We will now present some of the main findings, while more details will be available in the article and the respective supplementary materials. While we discussed some of the overall category counts above, particular categories might have become more or less prominent over time. We can thus consider the temporal distribution for each category normalized per respective year. We can notice the stable interest for domain applications in ML and AI and text data, which could be expected based on the strong support for these categories in the survey data. Another interesting example is that the entries included in the past several years demonstrate strong interest for neural network approaches for embedding calculations compared to the other computational methods. Another perspective to consider is whether the categories tend to co-occur in particular patterns or if they tend to compete, so to speak, and lead to exclusion of other categories. Here we present the results of Pearson's linear correlation analysis with pairs of categories. The shades of blue indicate positive correlation, while orange indicates negative correlation. Some of the interesting results include, for example, the rather strong but far from perfect correlation between the use of explicit visual representations and interaction techniques. Other examples include the application domain of computing and graph input data, or support for embedding vectors with less than 50 dimensions, and approaches agnostic to the input data type. With regard to negative correlation results, we could mention the competition between text and graph data types, the visual analytic tasks of representing and explaining model results, and the task of model results representation versus the ML AI domain, which is related to the support for other competing visual analytic tasks with that domain. While correlation analysis allows us to investigate relationships between pairs of categories, we are interested in patterns involving more than two categories at a time. We have thus applied the frequent pattern mining algorithm FP-GROWS to uncover the occurrences of such patterns. According to the results and focusing on largest pattern sizes, we can describe the following profile of a visual analytic technique involving embeddings. It's designed for the AI/ML domain, using neural network approaches for embedding computations, while not specifying explicitly the size of respective embedding vectors, supporting the visual analytic task of comparison or selection, explicit visual representation of embeddings or derived results and interaction with them, while discussing evaluation of such human-centered aspects in the respective publication. This pattern is supported by 9 entries in our data. Shorter patterns occur more frequently, with up to 15 entries supporting the pattern of the AI/ML domain, text input data, neural networks, and interactive visualization and evaluation concerns. The analysis presented in the previous several slides are based on the categories as annotated by us for the survey data. We actually provide further analysis in the article that we cannot go into detail due to the time restrictions, but we should mention that those results include topics extracted from the publication abstracts, authorship statistics, and also co-authorship network analysis, which might be interesting for the researchers within the visual analytic community.
Alright, to sum up with all the previous discussions, we would like to spend several minutes giving an overview of the current state of the art in using embeddings under visual analytics context, and highlighting some of the challenges and potential research opportunities. We want to make a summary from 2 aspects. The first is embeddings for visual analytics, which refers to integrating embeddings into a VA system such that it is beneficial to some high-level visual analytical goals and influence the whole system. And second, visualization for embeddings, which refers to using VA techniques to understand the embedding space or interpret the embedding process. We already saw several examples across different fields, such as healthcare data visualization or sports visualization. Embeddings are definitely beneficial and plays an important role in those VA systems in 4 aspects. First, it helps create an abstraction in the vector space for raw data of various types. We could expect more papers in the future using embedding methods to find and represent heterogeneous but joinable datasets for various downstream domain applications such as urban science, which naturally acquire data in different formats when creating a visual analytics system. Secondly, embeddings function as a bridge to the underlying raw data so that expert users can perceive global data distributions. When they perform operations at some other panels, the embedding views can function as a reference panel for validation purposes. Of course, there's a trade-off that adding an embedding view could help in operation validation and adding credibility to the system by linking back to the original data. But it also means adding additional layers of knowledge prerequisites for domain experts to learn and use the tool effectively. The third point we want to argue is that embeddings are often used as an interaction launchpad that triggers a series of user actions to happen. By generating clusters in the embedding space, users are able to navigate to areas of interest or lasso select a bunch of points to perform further inspection. However, the stability of the clustering algorithm and the choice of hyperparameters might be influencing the stability of the visual layout. The last point is that embeddings, especially word embeddings, are widely used to give recommendations to users on the next exploration targets. We believe there is much more potential in providing personalized guidance using embedding-based closeness metrics, and a wide opportunity to decide how to communicate and incorporate guidances to users in the existing visual interface. From another perspective, visualization for embeddings, which refers to visualizations that aim to explore or explain embeddings, we notice two challenges. First is about providing exploration at multiple levels. For the same dataset, embeddings can be generated at multiple levels, such as word embeddings, document embeddings, or concept-level aggregations. We believe there is much more research to be done in comparing embeddings at multiple levels and guiding users' navigation in a hierarchical fashion at different resolutions. Secondly, we mentioned multiple times the term multimodality. Even though many visual analytics systems analyze multimodal data, it is not common for authors to project them into a joint embedding space for exploration, nor to say there exist many papers focused on customized visual exploration and interaction, such as linking and brushing of such a shared multimodal semantic space. In summary, we would like to ask two questions for you, our audiences who happen to watch this part of the video. We know that embeddings are very useful in providing recommendations to users on potential objects to be selected. Then, how could we make the guidance adequate? In other words, how much freedom and influence do we want to give to the users? Given the user selection, to what extent we can shrink or expand the list of potential available selection candidates? Second, from a visualization for embedding perspective, for the same set of data, how could we aggregate different embedding spaces for comparison? And could we use some ensemble methods to determine the layout when visualizing such embedding spaces? All the previous questions and discussions have an assumption of creating whatsoever objective tools, but it is also important to be mindful to the potential biases hidden by those embedding representations. Biases in language embedding models have been widely discussed topics in natural language processing, computational linguistics, and other areas, but not many papers in the visual analytics plus embedding setup mentions or consider it in their design process. Even though there are few papers in our dataset focusing on visualizing bias patterns in the embedding space, still, for the majority of visual analytics systems using embeddings to give recommendation to users or as the basis representation of the data, it is crucial to at least acknowledge the presence of bias. Furthermore, since we classify papers in different domains, actually there exist many papers whose implicit target audiences are decision makers, companies, and governors. Further perspectives and considerations of biases beyond the purely analytical ones are definitely needed. The intention of many authors to use embeddings is trying to get a truthful representation of the collected data. But does the final visual representation really reflect truthfulness? As we discussed, not all papers give some number of the output embedding dimensions. Even a smaller set of papers mention how their embedding models are trained, fine-tuned, and evaluated. We are not sure if a small change in the hyperparameter choices or changes in the training data will influence the final visual layout dramatically or even convey a different message. As a result, we think it is important to add transparency to the embedding process by not only adding computational specifications in their paper, but also think about maybe integrating and visualizing both before and after rather black box embedding process. More often than not, computing embeddings is just one step out of many other things happening in the paper. But it is one of the fundamental steps for data transformation, and all other analytics are based on it. Moreover, the trends that many paper uses to calculate nearby items and generate recommendations means that it is influencing in the system, not in a trivial way. As a result, we would like to highlight the user-centric explainable artificial intelligence considerations. Even though not all embedding methods we surveyed are AI-based, but based on our statistics, we believe it is valuable to specify users' background and roles in using such a system, together with give justification on the computational details to ensure the reproducibility of the system. Lastly, we want to reiterate those 5 takeaways to conclude this talk. Based on our research, we believe that the use of embeddings in visual analytics is a hot topic. The number of VA papers using embeddings is increasing rapidly over the years. We observed great diversity in application domains, as well as diverse publication venues on this topic. Based on our annotations, we like to argue for the authors to describe your target users explicitly and describe the supported embedding process explicitly. When thinking about visually representing embeddings, the use of scatter plots and dimensionality plots are predominant, so there is definitely a lot of rooms for further contributions in how to create novel visual representations of the embedding space and how to integrate information retrieved from the embedding space into proper guidance of user interactions. Alright, that's all the content for this video. Thank you so much for your time and attention. There are much more details and examples in our survey article and in the survey browser, so please, if you are interested in any aspect of this topic, please visit this link, scan the QR code, or search for our paper titled VA plus Embedding Star. Feel free to contact me at this email address shown on the screen. I'm more than happy to discuss any questions, comments, or concerns about our work. Thank you.